Dave Bryla from USDA-ARS in Corvallis is going to, if I can find it, there it is, is going to be talking about heat damage in blueberries. Laser, forward back, and just, you don't have to get too close to my key. Time heads up.
Yeah, I can give you one.
5 minutes or something like that.
Hi, everybody. Today I'm going to talk about a new project that we're doing, looking at heat damage in blueberries. For those of you who know me, my specialty is nutrition and irrigation. So looking at irrigation practice to reduce heat damage is, kind of fits very nicely. So this project was funded last year by both the Oregon and the Washington Blueberry Commissions. Cooperators on the project include Julie Terrar, who's in our unit from Corvallis, but she's located in Prosser, Washington, and a new student working with me, Joy Yang, who's primarily the person who's taking all the measurements. So fruit cooling is often done in blueberries using sprinkler irrigation, and the idea is that it reduces the crop temperatures. Well, there's a number of ways in which water can be used to cool a crop. The first is called hydrocooling. Basically what this is just the actual contact of the water with the fruit. So you're adding cool water to warm fruit and it draws the heat out. The second is called convective cooling, and what this is the evaporation of water in the air, never actually touching the plants, but the evaporation creates air movement, and that air movement tends to cool the fruit. And the third is actually evaporative cooling from the plant surface or the fruit surface, where the water evaporates from the fruit, or it could also evaporate from the soil and cool the canopy. Now, of these three methods, the hydrocooling, or where you're actually contacting the water to the plants, tends to use the most water. It requires over 40 gallons per minute of acre of continuous irrigation for it to be effective at cooling. And we know this from other crops like apple, for example. So it's very effective at cooling, but it's very inefficient in its water use. The process that uses the least amount of water is the convective cooling, or that evaporation in the atmosphere itself. In this case, misters would be a good example of a convective cooling process, and typically it uses less than 30 gallons per minute. But the problem with convective systems, as we've seen from Lionel's talk earlier today, it requires a separate system for irrigation. So often if you have a misting system that's not good enough for irrigating, so typically you'll have drip system coupled with the misting system. And then finally, pretty much what has been used historically to cool blueberries in Oregon is the evaporative cooling process, where essentially what they do is they pulse their systems, so they'll turn it on for 15 minutes, leave it off for a half hour, turn it on for another 15 minutes. So in that case, they're using the combination of the hydrocooling with the evaporative cooling. In this case, it requires about 25 to 40% more water than your regular irrigation would use, and you would irrigate typically at night and then use the cooling during the day. Now, there are no guidelines for cooling in blueberries, so that was the reason why we wanted to do this project. Now, the current guidelines for cranberry is to run the sprinklers for at least an hour of continuous irrigation until the temperature drops below 85 degrees Fahrenheit. Well, if we were to do this in a blueberry field, we would clearly over-irrigate and we would flood the soil too much. So, example of the hydro or evaporative cooling is the sprinklers that was commonly used in Oregon. So the survey in 2001, about 90% of the fields at that time were irrigated by overhead sprinklers. So a lot of crops at that time were being cooled using these sprinklers, but now we have more and more fields being planted with drip. Well, now we're starting to see more problems with heat damage too. So what some growers are using with their drip irrigation is the convective cooling systems, or using misters. So here's a picture of that mister systems. Now, the closest research that has been done with fruit cooling that would be relatable to blueberry is a project that was done in California in the Napa Valley on wine grapes by Greenspan. And what he had done here is he compared overvine cooling misting system to an undervine misting system. And you can see on the bottom left that basically with the control, temperatures were higher every day than they were with the undervine cooling, and even cooler if they used the overhead cooling. So you had about a 10-degree drop with the overvine cooling and about a 5-degree drop with the undervine cooling. And looking at the temperatures in the canopy, the cordon, and the clusters itself, you could see that basically the overvine or the overhead cooling was more effective in general than that undervine cooling. But in grapes, it's very important, I think, to keep the grapes as dry as possible, so that's why they want to use something like a mist rather than sprinklers, because they do have huge problems with botrytis. So something that would work under vine would be particularly useful because you wouldn't have the issues with getting water on the fruit and increasing that humidity. So some questions that we have regarding cooling in blueberries is, first of all, at what temperature does heat-related fruit damage occur in blueberry? We don't even know at this point at what temperature that happens. We also don't even know what causes the damage. Is it temperature? Is it sunlight? Or is it a combination of both? So something like blackberries, for example, we see sun damage. In that case, it's probably more likely due to sun damage, the UV radiation itself, rather than to the temperature. Blueberries, I don't know. It could be temperature or sunlight. My guess is it would be more of a temperature issue in blueberries because they do have that waxing coating that would probably protect them from the UV, but that's one thing that we're interested in looking at. We want to know, do sprinklers and misters really reduce damage? How long and how often should you run the sprinklers and misters if they do work? Are there differences amongst cultivars? Could we be planting cultivars where you don't have the cooling system that wouldn't really require it as much as those where you do have the availability of cooling systems? Does cooling cause problems with fruit splitting? That's one concern that we have with applying water to a crop, and that we may potentially split the surface of the fruit, damaging it. Does it increase problems with plant disease? Of course, we're raising humidity, so we might be causing problems with pathogens. You're going to have runoff and leaching. We need to develop practices to reduce that and avoid flooding. And does it alter the harvest date, or does it even also alter the quality of the fruit itself? We may be improving the quality of fruit with cooling that we wouldn't even realize if we don't do the comparison. So the student working on the project, as I mentioned, is Joy Yang. She just started this past year. And some of the objectives that she's come up with to look at for her PhD dissertation include identifying what are the critical temperatures in which overhead cooling is needed. So trying to zone in, okay, when should we turn those sprinklers on and when should we turn them off when it's warm out? What she's trying to do is you see here with the data logger with lots of thermocouples measuring temperatures. She'll be measuring the weather conditions, and she's going to try to develop a model. So basically look at temperatures and humidity and sunlight from day to day, and try to use that information to make a prediction of when the sprinklers need to be turned on to be effective at cooling and when they could be turned off so you're not wasting water. She wants to look at the effects of fruit cooling on fruit quality and harvest date and identify cultivars that benefit the most from cooling. So she'll look at various cultivars and see which ones basically have the biggest reduction in damage by cooling. She also wants to identify any problems associated with cooling, looking at the disease, looking at what's happening in the soil water, see if there's any flooding happening, and to also investigate strategies for reducing heat damage without overhead cooling. So there's going to be a lot of fields out there that are currently now irrigated by drip, don't have sprinklers, don't have misters. Are there some other things that we could be doing? For example, are there mulches we could be using to reduce the temperature of the canopy? Are there pruning practices that we can use to reduce the problems that we have from heat damage? Now, here's some pictures of heat damage on the right. You see a sunburned fruit, which is pretty common. Obviously, that's not a marketable fruit. One thing that Joy is thinking, well, how we manage our canopy could have a big effect on how much heat damage we're getting. Because if you have lanky canes, or you have too much crop load that's bending those canes down, you're going to have more exposure to the sun. So why is that important? She's also finding that the damage not only occurs in the ripe fruit, but it's occurring early on during green stages of development. And we don't even see it at these particular stages, and we're finding it shows up later on as the crop develops. So that tells us that we need to be protecting these plants, not only when the fruit's ripening, but perhaps prior to these dates. She looked at the difference between the sun-exposed and the shaded fruit. So in this particular instance, on July 11th, 2013, at 3 p.m., the air temperature was 89 degrees. Well, in the sun, the temperature of the fruit itself was 20 degrees higher than what that air temperature was, so it was considerably higher. In the shade, on the other hand, it was almost the same as the air temperature, telling us that, so if we can keep these fruits shaded, perhaps by canopy management, we really don't need to worry so much about cooling the fruit in order to prevent heat damage. Here is some actual data that she collected with the data loggers comparing the sun exposed to the shaded fruit. So we see here on top the fruit exposed to the sun versus the air temperature in the shaded fruit. And you can see that the shaded and the air temperature fruit each day, so here we have the sun comes up, temperatures warm up. You can see in the shade they're pretty much the same as the air temperature, whereas those exposed to the sun are about 10 degrees warmer each day. So sun exposure, of course, is going to cause a lot more damage than shading fruit. And here's another set of measurements that she took to try to figure out, okay, so how warm is that fruit getting, not only on the surface, but within the fruit? So she put thermocouples under the skin of the blueberries and also put it near the center. And what she found, that the temperatures were actually, they were a little bit lower with the internal temperature as opposed to skin temperature. There was about 1 degree Celsius or about 2 degrees Fahrenheit difference. But there weren't a lot of difference between the center and the surface of the skin. So what that tells us is that this damage may not only be a surface damage, but it could be happening internally. Well, internal in a blueberry fruit are the seeds. If the seeds are becoming damaged, seeds is what's responsible for fruit size. So if we're damaging the seeds internally, we could be reducing the size of our fruit at harvest. She looked at east and west facing sun-exposed fruit. Very little difference here. Of course, the east side got warmer. The east and west, they pretty much got to the same temperature around the same time. But on the west side, they tended to get maybe a little warmer, stay warmer longer than they did on the east side of the row. We're able to use some existing irrigation studies that we have in Corvallis, Oregon, at the Lewis Brown Farm. So here's a field of Elliots in which we have drip irrigation plots. So we have 6 rows of 30 feet each, irrigated by drip, versus 6 rows irrigated by sprinklers, 2 different cultivars, Elliott and Duke, and then drip again. So what this allows us to do is to make some comparisons now between fruit where we're protecting them with the sprinklers versus the temperature that's happening with the drip plots. So here's a graph on August 5th of the Elliott fruits, and what we see here is that we have our air temperature increase during the day. Well, without any cooling at all, you could see again that the fruit in the drip irrigated plots were much warmer, about 20 degrees Fahrenheit warmer than the air temperature. So they were getting quite warm here. They were getting about 110 degrees. Whereas with the sprinklers, you could see each time she turned those sprinklers on, so every hour she turned it on for 15 minutes, you could see how that temperature drops. She turns the sprinklers off, they go back up. So it's pretty clear that the sprinklers is having quite a big effect on reducing the temperature of the fruit. It's also interesting, though, too, is that if you look at even prior to turning on the sprinklers, we see that the temperature of those fruit is actually cooler than the air temperature, whereas in the drip plots, the air temperatures is lower than the fruit temperature. And what happened here was she irrigated that evening prior to taking these set of measurements. So what's happening is the soil evaporation is also lending effect to cooling that fruit. So now as we go to planting more and more acreage with drip, we can see that we're really changing the dynamics of what's happening in our fields with temperature. And we do expect then, as a result of this, we're going to start seeing more problems with fruit damage. We're also, of course, going to see more problems with fruit damage as we plant in warmer areas such as eastern Oregon and Washington. So another thing that she's trying to do is, okay, well, let's look at history. Let's look at what's available so far. We have these incredible networks of agricultural weather stations throughout the Pacific Northwest that gives us information hourly. We also have information from Pure Bowl's website that tells us, okay, we saw problems with heat damage on these days and so forth. So we can start zoning in what conditions led up to the damage. Because what we're thinking is, it's not only the critical temperatures that we reach on a given day that might be causing the damage, but it's what happens prior to those temperatures. So what she's doing is she's going through, looking at the data, trying to figure out, okay, so how many times do we see events where the temperatures exceeded 30 degrees or 86 degrees Fahrenheit or 95 degrees or 104 degrees? And you can see, rarely, it's very rare that we ever see an instance where it goes as high as 104 degrees. So probably where we're trying to zone in here is somewhere between this 30 and 35 degrees or 86 to 95 degrees Fahrenheit where the problem is. And she's also looking at, okay, what's happening prior to that. So she's looking at changes in temperatures from one week to the next. And you can see these events are even rarer, but these may be the particular instances where we tend to see a lot of fruit damage. And then she's looking at the daily temperatures basically from one day to the next. So over time, she'll be able to take this information and perhaps give some better parameters in which to start testing, okay, when should we be turning our sprinklers on versus turning our sprinklers off, and developing this model for heat protection in blueberries. So right now, as I said, this is a very early study. It's a long-term study. It's going to go on for the next 4 years at least. But what we've found so far is that, not surprisingly, fruit exposed to sunlight have much higher temperatures than shaded fruit. Well, that tells us, though, that if we're not managing our canopies really well and we're exposing a lot of that fruit to sunlight, well, we're going to have a lot more potential for heat damage. So good pruning practices is very important. Internal fruit temperature is similar to skin temperature, so that damage is not only occurring at the surface, perhaps, but internally in the fruit, which could not only be affecting, okay, the cells in the skin, but are we affecting perhaps the seed development within the fruit? We're finding that the damage can occur in both green and ripe fruit, and in the case of the green fruit, we don't necessarily see that damage in the green fruit until that fruit turns blue. So this is telling us that we need to be protecting our fruit at various stages of development, not just during the ripe stages. Sprinklers are very effective at reducing fruit temperature, so now what we need to do is to develop good guidelines. Okay, at what temperatures do we need to turn those sprinklers on, and how do we need to operate them to be effective? So how long should we operate them, and how long can we shut them off, so that we're not using excessive amounts of water either as we use the sprinklers for heat protection. And the other thing that we're finding is that the critical threshold for heat damage is fairly low relative to the other crops, and it's dependent on temperature prior to hot weather. So again, I'd like to acknowledge the Washington Blueberry Commission, the Oregon Blueberry Commission, who partially funded this project. And I'd also like to point out that this work couldn't be done without help from Bill Sabo and Benito Mendoza and their crew, who do basically all the pruning and harvesting in our fields and allow us to continue this work. So with that, I'll take any questions if there are. Yes?
You mentioned, Dave, the temperatures conditions prior to the heat event. It seemed to me that we had a lot of sunburn last year because we had the last week of June very wet, cool weather that seemed to reduce the cuticle, and then we all of a sudden got some very hot weather.
Right.
So is that something that we should be taking into account as well in this?
Yeah, I think so. I mean, I think that is key, is that when you get these cool periods, and all of a sudden the temperature increases 10 degrees in a couple days, well, that tends to be when we see the most fruit damage. One thing that Joy is doing, I didn't show any of this results yet, but she's actually looking at the thickness of the skin, the thickness of the waxy cuticle layers under different temperature conditions, as well as in drought stress versus not drought stress plants. And she's looking at it using electron microscopy. So she's looking at it at a very, microscopic scale. So yeah, we will get that information hopefully, in the next couple of years. But that's part of this whole process of developing this model. Yes, Tom.
Dave, are you guys looking at any type of nutritional factors or foliars that might affect the sunburn? Or?
At this point, we're not looking at nutritional factors. The only thing like I mentioned, we don't even know if it's a temperature effect or a UV effect. So one thing we're going to be doing is using some UV filters and to try to sort that out. And we're also copying what Julie Terrar's design, where she's used this in wine grape, where she has an air conditioning unit and heating units, and she can control the temperature of individual berries. So we can get at that. But actually relating that to nutrition, no, we haven't really thought about that at this point. Yeah, sure. The shading would obviously work, and there has been a little bit of work actually done in Chile on that. As far as putting something on there to protect the fruit, is that what you're talking about? Yeah, I mean, there are things that they use, for example, in apple, but the problem with blueberries, we don't wash the fruit, so we can't wash a lot of these protectants off. So it would have to be, if it's a UV damage, we might be able to put some sunscreen on the plants, but we need to determine that first.
One question. I kind of did a little bit of kind of researching on it, using the mister compared to the drip, is that I find that the amount of gallonage that the mister calls for really kind of taxes your water system if you're trying to run large blocks of berries.
Right.
And one other thing I noticed is that like in real hot weather, the tips of the blueberry shoot will kind of blacken over. In a while I thought it was kind of blight, but then all of a sudden when the clouds come over, just like it's ready to kind of rain and the barometric pressure kind of got there, then all of a sudden everything went back into flesh growth. So in hot weather I find that I get a stunting of the growth.
Yeah, and that's the way blueberries grow too. That tip does die back, and then you get these flushes of new growth. I mean, it's kind of a unique growing system. But yeah, whether that's what we want to get at. So how much water do we need? We want to reduce the amount of water so that we're not taxing our systems. Perhaps at this point we have no idea when to turn these on. So you might be running your systems unnecessarily, or perhaps you are running when you need it. So the question is, can we cut back on how much we're running it, or do we need to design our systems differently, with more water availability for the cooling? Yes.
So your temperature data, half a dozen slides back, was that just during fruit set, or was that the whole season?
Most of that data, this particular measurement was taken in Elliott, so this would have been when the fruit was ripening. Again, this measurement again was in Elliott. It was the same data set, so it was the ripening fruit. And in this case, it was also ripe fruit, but it was done in blue crop. So I didn't mention the cultivars, but most of the measurements that I showed were on the ripening fruit.
Or the matrix with you had 3 different columns, 85,
Okay, this particular matrix, this is simply weather data that she's looking at this point. So this isn't reality. These aren't real thresholds at this point. We don't know what the thresholds are. What we're trying to do is just seeing, okay, if it were, say, a threshold of 86 degrees, how many times did that happen? Well, clearly it's happened a lot of times. So there's, and I don't think we had that much fruit damage going on during those periods. So it's unlikely that it's as low as 86. On the other hand, at 40 degrees, we see that it hardly ever happens in most locations. In this case, it doesn't need to get up that high, clearly, for the damage, because we know in 2012, 2013 in particular, we did see the heat damage, but we never got to those particular threshold levels. So we can see that we're zoning in somewhere between that 86 and 104. So she can go through a little, she can refine her search with the data and kind of get a better clue. But this is just to give us a clue at this point, but it's not a guideline. So I hope I didn't confuse you with that. Yeah. And exactly, I see what you're getting at now. You're saying, when were these data from? This was the whole season, right? And that's the other thing she needs to do.
It's cumulative number of days,
slow, yeah.
right, above that.
What's that?
A cumulative number of days of with high temperatures of the...
Yeah, and that was basically June through August that she did that. So obviously, we need to look at it monthly or even on a weekly basis. Yeah, thanks for noticing that.
Any other questions for David? Nope. Thanks, Dave.
Thanks.